steady state analysis of a pure inductance, right? So let us consider a pure inductance. Yeah, an inductive coil is excited by an AC supply here, right? So with a voltage of V, this is instantaneous voltage V, and when you apply a voltage of V, AC voltage, then a current I will flow in this circuit, and the voltage across the inductor we have defined as VL, and the inductance L of this inductor is given by this. Now, if you apply a voltage of sinusoidal voltage V is equal to Vm sin omega t, then the current flowing in the circuit is I, and the voltage across the inductor is VL, which is the same as V. So the voltage, yeah, is same as this one because there is no other element. Therefore, we say VL is equal to V, that is applied voltage. Then uh, let us find the voltage across the inductor, expression for the voltage across the inductor. Therefore, we know that already, we know the fact that the voltage across the inductor is given by this expression V is equal to L di by dt. This is VL, right? So the applied, since VL and V is are same, so we have equated to L di by dt. Since VL is di by dt, VL is given by dI by dt. And what is V here? V is nothing but Vm sin omega t. So Vm sin omega t is equal to L di by dt. And from this one, if you rearrange this equation in such a way that you take dt to here, right, and keep the L to the left hand side, then what we'll get is Vm by L sin omega t dt. You'll have di is equal to. So if you rearrange this equation, you will get this. Then ultimately we want the current I. So current, to know the current I, so integrate it here. So integrate on both sides. So you integrate on both sides here. Therefore, you will get if you integrated this di, you will get I, and if you integrated this, then what we'll get here it is Vm by L is a constant. Therefore, this will be brought outside, and you will get the integral sin omega t dt. So now, when you take the integral of sin omega t dt, so since it is taking integration with respect to dt, so sin omega t dt is nothing but minus cos omega t by omega. So the integral of sin omega t dt, since the integral variable here it is t only, therefore we got cos minus cos omega t by omega. So that we have substituted here. See here, right? And already we have Vm by L. So what we'll get here it is Vm by omega L, and this omega will comes here, right, into minus cos omega t. And this minus cos omega t, I can write it as sin omega t minus pi by 2. So using the trigonometric expression, so I write this minus cos omega t as sin omega t minus pi by 2. Then what we'll get here it is, so your I is equal to Vm by omega L sin omega t minus pi by 2. So now this entire Vm by omega L is a constant, therefore that I call it as Im. So your total current expression I is equal to Im sin omega t minus pi by 2. No, it is just simply looking like this. I is equal to Im sin omega t minus phi. It is like, where here it phi is pi by 2 only. So when an expression of any quantity is like this, and whereas the voltage expression here, we have what is the voltage we have applied? V is equal to Vm sin omega t. So when you apply a sinusoidal voltage to a pure inductor like this, the current in the inductor will also be a sinusoidal one, but with varying magnitudes. Im is given by Vm by omega L. Vm by omega L in the sign of omega t minus phi. So that means you have a phase shift. So you have a phase shift in the current. Phase shift in current. And what type of phase shift in current? Either the phase shift is leading or lagging. Since if you look at that, already we have discussed that when the expression is having a negative sign here, and this negative sign represent a lagging phase shift. Therefore, we say that current I lags V by 90 degrees. So from this simple expression that, so in a pure inductor, the current I lags the applied voltage V by an angle 90 degrees like this. So how do you represent that in the vector? So this is a vector diagram or phasor diagram. If you look at that phasor diagram. So in this phasor diagram, so V is equal to Vm sin omega t, and I you got it as Im sin omega t minus pi by 2 you got. Right. How do we represent this? V is equal to Vm sin omega t and I is equal to M sin omega t vector is, this is V here. So since V is taken as a reference, 0 degrees axis, and obviously if you look at the current vector is I, we have concluded that I lags V by 90 degrees. So lagging in the sense అంటే ఏమిటి అని అంటే since the vectors we know that vectors are moving in the counter clockwise direction. దీనికి ఈ వోల్టేజ్ వెక్టర్ ఎలా మూవ్ అవుతుంటే దీనికి లాగింగ్ అంటే కంపల్సరీ I vector should be here but with an angle of 90 degrees. Exactly. So this is the phasor diagram of a voltage and current in a pure inductor. And if you look at the waveform, so the waveform here of voltage and current, this is the voltage waveform, this is the current waveform. We can represent it that like this. See here, the voltage waveform is starting from 0 and attains a maximum at point some point and it comes to 0 here. And once again, so this is a sinusoidal wave. But whereas current, as we have know that from this expression, current is lagging by an angle 90 degrees. So ante ఇది 0 ఇది pi అయినప్పుడు this is pi by 2. So exactly at pi by 2 current waveform will start. After pi by 2 only the current waveform start and with a magnitude. This is Im. Im is different and Vm is different, right? So this is the lagging waveform, we can say, with an angle of pi by 2, right? So the waveform of voltage and current in a case of a pure inductor are shown in here. Then coming to the inductive reactance. So in the previous slide, we have I is equal to Im sine omega t minus pi by 2. You got it. This is the expression wherein Im is defined as Vm by omega into L. Generally, current, if you apply the Ohm's law, if you look at that Ohm's law, what does your Ohm's law states? Here it is. Ohm's law says the current I is equal to V by impedance or resistance and ante is it looking like this both are similar? Therefore, this omega L we call it as the impedance Z, and this impedance Z is called as inductive reactance. This is called as inductive reactance and it is represented with a letter called as XL. So XL is equal to omega L here, which is equal to which is nothing but the inductive reactance. It is like a resistance in pure resistive circuit. Therefore, this is also an opposing force for the current in case of a pure inductance. And this omega, already we know that omega can be represented as 2 pi FL. Therefore, the expression for XL, that is inductive reactance, is given by omega L or 2 pi FL. So as I mentioned earlier, it is equivalent to the resistance in a resistive circuit, and the units for this one is ohms. Then coming to the power. So we can calculate so many powers here. Let us first find out the instantaneous power. So instantaneous power, we always know that in case of DC circuit, power expression is voltage multiplied by current, V into I, where V is also here instantaneous value and I is also an instantaneous value. So what is V here? We already have defined it as V is equal to Vm sin omega t. This is your V. And I, in case of a pure inductor, when you apply V is equal to Vm sin omega t, what is the instantaneous value of expression of the current? Im sin omega t minus pi by 2. So therefore, the instantaneous power P is equal to, since V into I, so for Vm sin omega t into Im sin omega t minus pi by 2. Indulo Vm and Im are constants, so therefore I brought them to the one side here. Then sin omega t into sin omega t minus pi by 2 is nothing minus cos omega t. So that is why you got here minus sin here and cos omega 2. Then sin omega t and cos omega t, I can write it as sin 2 omega 2 by 2. So that is because you know that sin 2 omega t కి మన ట్రిగ్నోమెట్రిక్ ఎక్స్ప్రెషన్స్ లో మీకు చూస్తే యూ హ్యావ్ sin 2 omega t కి ఎక్స్ప్రెషన్ ఏమిటి అంటే 2 sin omega t cos omega t, ఇది ఎక్స్ప్రెషన్, రైట్? సో therefore మనకి ఇక్కడ ఉన్నది ఏంటి, sin omega t ఉంది కాబట్టి అప్పుడు sin omega t టు cos omega t అంటే sin omega t 2t sin 2 omega t by 2, అదే ఇక్కడ రాశాను చూడండి. అంటే దీన్ని ఇలా రిప్రజెంట్ చేసాం. సో దిస్ ఇస్ దట్, రైట్? సో ది పవర్ is equal to, this is an instantaneous power, please keep it in mind, not average power, right? Right, therefore which is equal to minus V into Vm Im by 2 sin 2 omega t. So as seen from this above expression, so this instantaneous power is also a sinusoidal one, right, with a frequency of 2 omega. అంటే మనం నిన్న క్లాస్లో చెప్పుకున్నట్టుగా పవర్ ఇన్ ప్యూర్ రెసిస్టెన్స్ కూడా, but it is positive, power is positive, but it is fluctuating, but the frequency of that fluctuations or the power, instantaneous power, is double the frequency of voltage and current waveforms. ఇక్కడ కూడా అంతే. సో పవర్, ది ఇన్స్టంటేనియస్ పవర్ ఈజ్ నెగటివ్ హియర్, చూడండి ఇక్కడ, అక్కడ పాజిటివ్ వచ్చింది కానీ ఇక్కడ దిస్ ఇస్ నెగటివ్, అండ్ the frequency of that instantaneous power is the double the frequency of the voltage and current of the pure inductor, right? This is about the, then coming to the average power. So we know that the average power can be determined by this expression, right? Power is equal to P average is equal to 1 by 2 pi integral 0 to 2 pi P. Actually, the power average expression, average power expression, is equal to 1 by 2 pi integral 0 to 2 pi P dt. or d omega t if it is d omega, where p is an instantaneous value. This is instantaneous value. Right. So therefore, that instantaneous value already we have determined the expression for that. That you substitute here. So that which is given by minus Vm Im by 2 sine 2 omega t and d omega t. And if you integrate it, this then substitute the limits, you will get the 0. Right. So the value of this average power, you will get the 0. Therefore, what from that one, what we can hear is the average power in a pure inductor circuit is 0. This is very important point to be noted. Or in other words, the power consumed by a pure inductance is 0. Actually, average power is nothing but the power consumed. So your inductor cannot consume any power like your resistance. Resistance consumes the power. So the voltage, current, and the power waveforms are purely inductive. For a purely inductive circuit are as shown in figure. This is the voltage waveform, right? This is the current waveform because this is lagging with a 90 degrees here, lagging. See here, and this is the power waveform. So the power waveform will be having a frequency of double the frequency of that. అంటే double the frequency అంటే మీరు చూస్తే కనుక చూడండి, వోల్టేజ్ వేవ్ ఫామ్ ఒక సైకిల్ కంప్లీట్ చేసేటప్పటికి పవర్ వేవ్ ఫామ్ ఈస్ కంప్లీటింగ్ 2 సైకిల్స్. చూడండి, పవర్ వేవ్ ఫామ్ ఇక్కడ స్టార్ట్ అయింది, ఇక్కడ నుంచి ఇక్కడ ఒక సైకిల్ అయింది, రైట్. ఇక్కడ నుంచి ఇక్కడ ఇంకో సైకిల్ అయిపోయింది. ఇదేమో సెకండ్ సైకిల్ అండ్ దిస్ ఈస్ ది ఫస్ట్ సైకిల్. సో ద పవర్ వేవ్ ఫామ్ ఈస్ completing 2 cycles when the voltage or current waveforms are completing 1 cycle. So that is why the frequency of the power in case of a pure inductor is double the frequency of the voltage or current. Now let us look at this phasor algebra for a pure inductive circuit. Now let us represent them in the phasor. Therefore, the applied voltage that V is equal to Vm sine omega t, I represent it as a phasor in the polar form. This is a phasor representation chapter 2. There are two forms. One is polar, another one is Cartesian or rectangular form. This is a rectangular form. Idemo rectangular form. This is a polar form. So every sinusoidal quantity or a complex quantity may be represented either in polar form or in the rectangular form. So your V is equal to Vm sin omega t is a complex quantity, and this can be represented as a vector V bar. General vectors V letter పైన గీతతో పనిచేస్తుంది, దీన్ని V bar అని అంటాం. Where that V bar is equal to V polar form లో magnitude. V is the magnitude, where this magnitude, you please keep it in mind, this must be an RMS value only. Right. Or in some textbooks, they also take Vm. Suppose if you write capital V, this indicates that RMS value only. Right. And what is the phase angle here? The phase angle in the expression is 0, right? 0 degrees. Omega t plus 0 కింద రాయొచ్చు కదా. అందుకని polar form లో this is V angle 0 degrees. And this can be represented in the rectangular form as V plus J0, where J is a complex operator. So the voltage, applied voltage, this is an applied voltage, and this applied voltage expression can be represented in the complex form like this, or in the phasors like this. Then current expression we have. What is the current expression? I is equal to, we have a current expression as I is equal to Im sin omega t minus 90 degrees. And this we can represent it like this vector. I bar is equal to I angle minus 90. This phase angle here it is minus 90 here, that you can represent it here. And this I, once again, you please keep it in mind, this is an RMS value. Right. And this can be, this is in the polar form, and this in the rectangular form is, this can be represented as 0 minus J I like this. So polar to rectangular, అది మనం నేను చెప్పుకున్నాం, polar నుంచి rectangular మార్చాలనుకోండి, I angle minus 90 ఉందనుకోండి, this can be represented as I sin 90, sorry, I cos 90 plus J sin 90. So likewise, we can represent it, so minus 90, J sin minus 90. Right. Therefore, cos 90, since cos 90 is 0, and minus J I, yeah, I. So sin of minus 90 is minus sin 90, and which is equal to 1. So that is why the rectangular form of the current is represented in this one. Then when you want reactance, that is XL if you want. So what you do, applying the Ohm's law, V by I, you substitute V bar by I bar, and V bar is nothing but V angle 0 degrees, and I bar is nothing but I angle minus 90 degrees. And then you will get XL. What is this XL? The magnitude of XL is nothing but V by I. and ఈ యాంగిల్స్ 0 and -90 అంటే -90 పైకి వెళ్తే ఏమవుతుంది +90 అవుతుంది. Therefore the XL angle 90 degrees is the impedance or reactance, inductive reactance. Right. So this already I told you earlier, this 90 degrees can be represented as J operator into XL. దీన్ని ఇలా రాయొచ్చు like this. -90 అంటే -JXL కింద రాస్తాం. Right. So అలా రాస్తే మనకు వచ్చింది ఇదే. This is about the voltage expression. The V bar is equal to I bar into J times XL. This is the phasor algebra of a pure inductive circuit. Now let us take this simple example to illustrate the different to determine the different quantities in the pure inductor. Let us take this example. A pure inductive coil allows a current of 10 amperes to flow from 230 volts, 50 hertz supply. Find the inductance of the coil, power absorbed, and equation for voltage and current. So first ఇది ఏమిటి మనకి ఇండక్టెన్స్ ఆఫ్ ది కాయిల్. ఇండక్టెన్స్ అంటే జనరల్లీ ఎల్ అంటాం ఇండక్టెన్స్. సో ఎల్ తెలియాలంటే ముందర ఎక్స్ఎల్ ఫైండ్ అవుట్ చేయాలి. అంచేత లెట్ us see that ఎక్స్ఎల్కి ఏమిటి ఎక్స్ప్రెషన్ ఎక్స్ఎల్ ఈజ్ ఈక్వల్ టు వి బై ఐ. సో వాట్ ఈస్ వి? వి ఈజ్ ఆల్రెడీ గివెన్ as 230 volts. This is RMS value. Please keep it in mind. And this is I, 10 amperes. This is also RMS. So the applied voltage and applied current are 230 and 10. Therefore 230 by 10 will give you 23 ohms. Therefore the inductive reactance is given by 23 ohms. And once you get inductive reactance by using this formula, XL is equal to 2 pi F into L. You can find out the L. In this one, frequency is 50 hertz. Here he has given F is equal to 50. Substitute F is equal to 50 here. Then pi 2 and XL is now 23 ohms. Therefore from that one, L is equal to XL by 2 pi F, which is about around 0.073 henries. Now the second bit is power absorbed. So already we have derived the equation of an average power in a pure inductor is 0. Therefore here straight away same expression we can write it here. Then the third one is equation for voltage and current కావాలి. అంటే voltage కి current కి equation కావాలి. ఇక్కడ మనకి ఇచ్చిన voltage ఏమిటి? This is VRMS. V means VRMS. Therefore which is equal to 230 volts ఇచ్చారు. So from that one actually మనకి voltage expression ఏమిటి? V is equal to VM sin omega t is the applied voltage. ఇందులో మనకి Vm కావాలి, omega కావాలి. Omega is equal to 2 pi F. So what is 2 pi F for 2 pi into 50? So which is given by 314 radians per second, that is omega. Right. Then you want Vm. So Vm, how do you find? In the last class, we have seen that the relation between VRMS and Vm is equal to VRMS is equal to Vm by √2 అని మనం for a pure sinusoidal waveform, the relation between the maximum value quantity and the RMS value is given by this. VRMS is equal to Vm by √2. From this one, can I able to find out Vm? Vm is equal to √2 times VRMS. And the same expression here we have used to see here. This is √2 into VRMS. What is VRMS is 230. Therefore, if you substitute that, you will get Vm as 325.27 volts. And once you get the Vm, Im also can be determined. Im is nothing but √2 I. So what is √2 I? This is IRMS. IRMS already given is IRMS has given as 10 amperes here. IRMS is given, and that you substitute here. √2 into 10 will give you 14.14 amperes. So once we get the Vm, Im, then the voltage expression is given by V is equal to Vm sin omega t, and current expression I is equal to Im sin omega t minus pi by 2. So where Im is already we have calculated as 14.14 and Vm we have calculated as 325. And if you substitute that, you will get the voltage expression as this and current expression as this. So likewise, in a pure inductor, you can find these quantities.